There is a storm on Jupiter that has not stopped raging since before Isaac Newton was born. It is wider than 3 Earths placed side by side. Its winds exceed 640 kilometers per hour, and it reaches down into the planet's atmosphere to a depth of 500 kilometers, deeper than the distance from London to Edinburgh, with no sign of a flaw beneath it. And yet that storm, the most famous weather event in the solar system, is not the thing that stopped NASA scientists in their tracks. What stopped them was what they found beneath it. For 3 centuries, we assumed we understood what Jupiter was. We were wrong about almost everything, not partially wrong, not slightly wrong, cosmically, fundamentally, structurally wrong, in ways that forced a rewrite of how we believe planets form, how magnetic fields are born, and whether the chemistry of life might be far more widespread in the universe than anyone had dared to suggest. Jupiter is not a planet in the way you intuitively understand a planet to be. That is the first thing worth establishing clearly, because everything that follows depends on it. When you picture a planet, even a gas giant, there is an instinct to imagine something with a surface, or at least a well-defined interior, layers stacked neatly like a geological cross-section from a school textbook, each region transitioning cleanly into the next. Jupiter refuses that mental model at every step. Start with scale. Jupiter contains more mass than all the other planets in our solar system combined, and then doubled. Its diameter stretches 139,820 kilometers from pole to pole, which means that if you hollowed it out and tried to pack Earths inside, you could fit approximately 1,321 of them. Its mass is 317.8 times that of our entire world. These are not merely large numbers. They are numbers that bend the rules. At sufficient mass, hydrogen, the most abundant element in the universe, the same wisp of gas you breathe past without registering, begins to behave in ways that simply do not occur anywhere on Earth's surface. Yet for all its enormity, Jupiter formed from the same cloud of gas and dust that produced the Sun, the Earth, and every other body in our solar system. It formed earlier than the others. Planetary scientists believe it assembled within the first 3 to 5 million years after the Sun ignited, racing to accumulate material before the solar wind swept the raw ingredients away. It grew so quickly and so voraciously that it consumed most of the available heavy material in the inner solar system, effectively sculpting the formation environment in which Earth itself would eventually arise. Without Jupiter's gravitational dominance deflecting incoming asteroids, the rate of impacts on early Earth would have been dramatically higher. Some researchers argue that without Jupiter, complex life might never have had the time to evolve here at all, so Jupiter matters. Not as an object of curiosity, not as a pretty backdrop for space photography. It matters as the keystone of our solar system's architecture, the planet whose formation determined everything that came after it. And this is why, when a spacecraft called Juno arrived at Jupiter on the 5th of July 2016 and began measuring what was actually inside it, the scientific community's reaction was not excitement. It was in many cases confusion, followed swiftly by the particular, humbling sensation of realizing that everything you thought you knew had been built on assumptions rather than evidence. To understand the scale of the surprise, you need to understand what the models predicted and why scientists were so confident in those predictions for so long. For most of the 20th century, the standard model of Jupiter's interior described a planet structured in 3 broad zones. The outermost region was the atmosphere, that famous swirling tapestry of orange, white, cream and brown bands, the product of ammonia ice crystals, water clouds, and organic compounds being churned in winds that exceed anything recorded in Earth's weather history. Beneath that, theory suggested, the pressure would compress hydrogen gas into a liquid state. An ocean of hydrogen, the largest ocean in the solar system, stretching to a depth of roughly 20,000 kilometers. Below that, the pressure was so extreme, millions of times greater than Earth's surface pressure, that hydrogen would undergo a phase transition unlike anything in our ordinary experience, becoming liquid metallic hydrogen, a substance in which electrons are stripped free from their atoms and flow through the material like a conducting fluid, generating Jupiter's colossal magnetic field. And at the very centre, the models predicted a compact, rocky core, perhaps 10 to 40 Earth masses of heavy elements, iron, silicates, ice, compressed to unimaginable density, the original seed around which all that hydrogen had once accreted. It was a tidy model, elegant even, and it was constructed from mathematics rather than measurement, because no instrument, no telescope, no probe had ever been able to peer deep enough beneath Jupiter's clouds to test it directly. That changed with Juno, and the model did not survive contact with reality. But before we descend into what Juno found, we need to spend time on what makes Jupiter's interior so extraordinarily difficult to see, because the cloud layers that shroud it are not merely a visual inconvenience. They are a scientific barrier of genuine ferocity, and the story of how engineers built a machine capable of penetrating them is a story worth telling in its own right. Jupiter's clouds are not like Earth's clouds. I want to make that distinction sharply, because the word clouds carries domestic connotations. Cotton-white formations over summer fields, afternoon showers, the kind of weather you can see from a window. Jupiter's cloud system is something else entirely. It is a layered, interlocked atmospheric structure of tremendous depth and complexity, and it has for centuries acted as one of the most effective screens in the solar system. The outermost visible layer, the one captured in every photograph taken by Hubble, Voyager, and every amateur telescope pointed at the night sky, is composed primarily of ammonia ice crystals. The temperature at this level hovers around -110 degrees Celsius, and the ammonia freezes into pale yellowish-white formations that catch the sunlight and produce those familiar bright zones you see in every Jupiter image. The brown and orange belt regions are areas where the cloud deck is lower and the ammonia layer thinner, allowing deeper, warmer, darker material to show through. This is only the uppermost tier of a system that extends far below. Beneath the ammonia ice layer lies a region dominated by ammonium hydrosulfide, a compound formed when ammonia and hydrogen sulfide react under pressure, producing a rust-coloured, thick particulate cloud that absorbs certain wavelengths of light and scatters others. This is the layer that gives Jupiter's belts much of their brown and orange coloration. Below that, at depths where Earth's entire atmosphere would have been compressed into nothing, lies a water cloud layer, not liquid water as we know it on Earth's surface, but a dense, hot, pressurized vapor cloud system behaving somewhere between a liquid and a gas, under conditions that would vaporize most materials familiar to us. These three cloud decks together form a curtain through which ordinary light simply cannot pass. Every telescope ever pointed at Jupiter, from Galileo's in the early 17th century to the most sensitive space-based instruments before Juno, was seeing only the top of this curtain. The interior of the planet, the bulk of it, the 99.9% that lies beneath those clouds, was completely invisible. The 1995 Galileo probe changed things, briefly, and in a way that raised more questions than it answered. NASA's Galileo spacecraft, primarily an orbiter studying the Jovian system, released a small atmospheric entry probe that plunged into Jupiter's atmosphere on the 7th of December 1995 at a velocity of approximately 170 kilometers per hour. The heat generated during that entry, Mach 50, the fastest atmospheric entry ever attempted by a human-made object, reached temperatures of around 15,500 degrees Celsius hotter than the surface of the Sun. The probe deployed a parachute, slowed, and spent 57 minutes falling through Jupiter's upper atmosphere before the pressure crushed it. In those 57 minutes, it transmitted measurements of temperature, pressure, wind speed, and chemical composition down to a depth of about 120 kilometers, where the atmospheric pressure reached roughly 22 times Earth's sea level pressure. The Galileo probe found winds far stronger than expected. It found lightning, it found sulfur-bearing compounds, and then, to the dismay of the science team, it found almost no water, 10 times less water than even the most conservative pre-mission estimates had predicted. This was a problem. Water abundance in Jupiter's atmosphere is not merely a meteorological curiosity. It is a fundamental marker of how the planet formed and how much material from the cold outer solar system was incorporated into its bulk. The solar nebula models that had been developed over decades predicted that Jupiter should be enriched in water relative to the Sun. The Galileo probe suggested it was dramatically depleted instead. The science team, after considerable analysis, concluded that the probe had been unlucky. The entry site appeared, based on infrared observations from Earth-based telescopes, to coincide with a region of unusual dryness, a hotspot, a dry downdraft where material was being pulled down from higher in the atmosphere, carrying relatively little moisture. The probe had not sampled a representative slice of Jupiter. It had fallen into an anomalous chimney, or so the prevailing interpretation went. This is the Galileo water paradox, a measurement that didn't match the models, explained away by a sampling artifact that could neither be confirmed nor disproven with the technology available at the time. It sat in the literature for decades, a persistent source of discomfort, a number that didn't fit, filed under probably an outlier, but never definitively resolved. And it was not the only unanswered question. It was also the matter of Jupiter's magnetic field, a field so powerful and so structurally strange that it demands its own examination. Earth's magnetic field is generated by a process called the geodynamo. Convective motion of liquid iron in our planet's outer core creates electric currents, and those currents sustain the magnetic field. The mechanism is well understood in principle, though the details of Earth's own field are still the subject of active research. Jupiter's magnetic field is 14 times stronger than Earth's at the surface of the planet, and it extends outward into space for an enormous distance. Jupiter's magnetosphere, if it were visible to the naked eye, would appear in Earth's sky approximately 4 times larger than the full moon, even though Jupiter itself is merely a point of light. That is how vast the magnetic bubble around Jupiter truly is. Pre-Juno models predicted that Jupiter's field would be relatively smooth and symmetric. A dipole field, similar in basic structure to Earth's, generated somewhere in the metallic hydrogen interior. Those models were built on reasonable assumptions about how rotating electrically conducting fluid generates magnetic fields. They were also, as it turned out, significantly incomplete. The 2016 Voyager flybys, and everything that came before Juno, had hinted that Jupiter's field was irregular, but no one had measured it in sufficient detail to know how irregular. Juno's magnetometer suite, the most precise ever deployed to the outer solar system, was designed to map it in full, and what it found warranted a new category of strangeness. But the deeper mystery, the one that would take Juno's full instrument suite multiple passes to begin unravelling, was the interior structure itself. The jet streams, the depth of the storms, the nature of the core. These questions had been stacked up over decades of observation, unanswered not for lack of scientific curiosity, but for lack of a spacecraft capable of answering them. Juno was that spacecraft. But getting it there, and keeping it alive long enough to collect data, required solving an engineering problem that had no precedent in the history of space exploration. There is a reason we did not send an orbiter to Jupiter earlier. There are actually many reasons, but the most visceral one is this. Jupiter does not merely sit in space like a large, passive gas ball. It actively attacks the spacecraft that approach it. The source of this hostility is Jupiter's magnetic field. That vast magnetosphere, the same field that planetary scientists wanted so desperately to map, is also a particle accelerator of extraordinary power. Protons and electrons, drawn in from the solar wind and from material ejected by Jupiter's volcanic moon Io, are trapped and accelerated within the magnetic field to energies that make Earth's Van Allen radiation belts look comparatively benign. Jupiter's radiation environment is, by a considerable margin, the most severe in the solar system beyond the Sun itself. At the inner fringes of Jupiter's radiation belts, the particle flux is so intense that an unshielded human being would receive a lethal dose of radiation within minutes. Electronic components fare only slightly better. The semiconductor circuits that modern spacecraft depend on, the microprocessors, memory chips, and sensor arrays that handle data processing, navigation, and instrument control, are systematically destroyed by high-energy proton bombardment. Transistors suffer cumulative damage as particles punch through their crystalline structures, displacing atoms and introducing defects that degrade performance until, eventually, the circuit fails entirely. This is not a hypothetical concern. It is the primary engineering constraint that had defined and limited every Jupiter mission before Juno. The Galileo orbiter, which studied Jupiter from 1995 to 2003, suffered progressively worsening radiation damage throughout its mission. Its tape recorder, a critical data storage component, developed increasing problems. Its trajectory was carefully managed to minimize exposure to the most intense radiation zones, which meant that many of the most scientifically valuable regions near the planet remained off-limits. Juno's designers at Lockheed Martin, working with Scott Bolton and his team at the Southwest Research Institute, chose a different approach. Rather than trying to avoid radiation, they hardened Juno against it. Spacecraft's electronics were housed inside a titanium radiation vault, a roughly 1 centimeter thick titanium box weighing approximately 200 kilograms, encasing the flight computer, power control, command and data handling, and the telecommunications hardware in a structure that reduced the radiation dose to internal electronics by a factor of roughly 800. Titanium was selected over other metals because of its combination of density and structural strength. It is heavy enough to attenuate high-energy particles, while light enough to meet the spacecraft's mass budget. This vault was a genuinely novel engineering solution. No spacecraft had ever carried anything quite like it into deep space, and it worked. Over the course of its mission, Juno has survived a cumulative radiation dose that would have killed a Galileo-era spacecraft in its first few orbits. Bolton, during a press conference in 2022, put it simply, "We built Juno like a tank. Radiation shielding was only part of the challenge. Juno is a solar-powered spacecraft, the first in history to operate at Jupiter's distance from the Sun, roughly 5.2 times farther from the Sun than Earth. At that distance, sunlight is roughly 27 times dimmer than at Earth. To generate sufficient power from solar panels at Jupiter, Juno carries 3 enormous solar panel wings, each 2.9 meters wide and 8.9 meters long, giving the spacecraft an overall span from wingtip to wingtip of about 20 meters, approximately the wingspan of a small commercial aircraft. Those panels generate roughly 486 watts at Jupiter's distance, down from about 0 watts that the same panels would generate in Earth orbit. 0.486 watts is not much. A household electric kettle typically draws around 2,000 watts, but Juno's instruments were designed with exceptional frugality in mind, and the spacecraft manages its power budget with the same precision that an engineer manages a critical system operating at the edge of its envelope. The orbital design was equally carefully constructed to minimize radiation exposure while maximizing scientific return. Juno orbits Jupiter in a highly elliptical, polar orbit, plunging in from a distance of millions of kilometers, sweeping close over the cloud tops, then swinging back out again on a 53-day cycle. The polar approach allows Juno to pass over the planet's magnetic poles, sampling regions that previous equatorial spacecraft could never access. The elongated orbit means that Juno spends most of its time far from Jupiter, where radiation is manageable, and only a few hours in the intense near-Jupiter environment during each close pass. It is, in engineering terms, a brilliant compromise between scientific ambition and physical survivability. On its first close pass on August 27, 2016, Juno flew within approximately 4,200 kilometers of Jupiter's cloud tops, closer than any spacecraft had ever approached the planet, at a speed of approximately 208,000 kilometers per hour. The radiation detectors registered readings that pushed their instruments near the top of their measurement range. The team held their breath, and Juno came through intact, returning data that, within weeks, began dismantling the textbook description of Jupiter one layer at a time. The first revelation concerned the jet streams. For 3 centuries, astronomers had observed Jupiter's banded appearance, those alternating dark belts and bright zones girdling the planet like the stripes on a ball, and assumed they were atmospheric phenomena, weather, a relatively thin skin of activity driven by sunlight and internal heat convection, confined to the upper atmosphere, much as Earth's weather is confined to the troposphere. The bands were gorgeous, they were persistent, and they were widely assumed to be shallow. Juno's gravity measurements proved otherwise. By tracking the spacecraft's radio signal with extraordinary precision as it orbited Jupiter, detecting Doppler shifts in the signal that corresponded to tiny variations in the planet's gravitational pull, the science team was able to map Jupiter's interior density distribution with a resolution that had never previously been achieved. And what the gravity field revealed was that Jupiter's jet streams were not shallow. They were not superficial weather patterns. They extended to a depth of approximately 3 kilometers below the cloud tops, penetrating so deeply into the planet that they contained in total a mass equivalent to approximately 3 Earths' worth of atmosphere moving in organised, high-speed rivers of gas, 3 Earths circling Jupiter. In the form of jet streams, Scott Bolton, presenting these findings in March 2018, described his reaction to the data as follows, and I quote his words not because the script requires a quote, but because scientists, in moments of genuine surprise, tend to reach for understatement. This discovery surprised the entire team. That, from a man who had spent 27 years building a mission to Jupiter, whose entire professional life had been oriented toward discovering something new, is a remarkable thing to admit. The team that built this mission to find the unexpected was still genuinely surprised when the unexpected arrived. But the jet streams were only the first layer of the onion, and each layer, as Juno peeled it back, revealed something stranger than the last. There was the question of the Great Red Spot. For 3.5 centuries, since at least 1665, when the Italian astronomer Giovanni Cassini made some of the earliest recorded observations of a persistent oval feature on Jupiter, the Great Red Spot had been one of the defining mysteries of the solar system, a storm larger than the entire Earth, rotating counterclockwise in Jupiter's southern hemisphere, persisting across centuries in a universe where weather systems typically last hours or days. What sustained it? What was its root system? What anchored it against the shearing forces of the surrounding jet streams? And how deep did it go? Juno answered the depth question in 2021, and the answer was sobering in its scale. Gravity measurements during a close flyby of the Great Red Spot indicated that the storm extends approximately 500 kilometers below the cloud tops. 500 kilometers. To calibrate that, the International Space Station orbits at an altitude of approximately 400 kilometers above Earth's surface. The Great Red Spot's root system is deeper than Earth's orbital altitude. It is not a surface weather event. It is a column of gas that plunges into Jupiter's atmosphere to depths that on Earth would qualify as outer space. And yet, even knowing its depth, even understanding its scale, we still cannot fully explain why it has persisted for so long, or why it is, over geological time, slowly shrinking. A storm that has outlasted every human civilization now living, still contracting toward an end that no one can predict. Which leads to the question that nobody expected Juno to answer, because nobody expected the answer to be what it was. The question of what lies at the very centre of Jupiter. The question of the core. The core model that had guided planetary science for decades was deceptively simple. Jupiter formed, the theory held, when a primordial rocky body accumulated enough mass, somewhere between 5 and 15 Earth masses of rock and ice, to gravitationally attract hydrogen gas from the surrounding solar nebula. Once the core reached a critical size, it entered a phase of runaway accretion, sweeping in enormous volumes of gas in a geologically brief interval. This process is called core accretion, and it is the dominant theoretical framework for explaining not just Jupiter's formation, but the formation of gas giants across the cosmos. The core would still be there, compressed to unimaginable density at the centre of the planet, an enduring relic of Jupiter's origin. This prediction carried with it a specific signature in Jupiter's gravity field. A compact, dense, well-defined core would create a measurable concentration of gravitational pull at the planet's centre, a gravity signal that, given sufficiently precise measurements, should be detectable even from orbit. Juno's instruments were sensitive enough to find it. By tracking the spacecraft's radio signal using NASA's Deep Space Network to millimetric precision, the science team mapped Jupiter's gravitational field to a degree of fidelity never before achieved in planetary science. If there was a solid core, Juno would find it. What Juno found was the absence of one, not emptiness. There was clearly something at the centre of Jupiter that was denser than the surrounding layers. But the gravity measurements refused to resolve into the signature of a compact, well-defined core. Instead, the data implied that Jupiter's centre is occupied by what researchers now call a dilute core or fuzzy core, a region where heavy elements are not confined to a small, dense sphere but are spread diffusely across an enormous volume extending from the planet's centre out to perhaps half its radius. Half the radius of Jupiter is approximately 36,000 kilometres. To put that in perspective, the entire diameter of Earth is 12,742 kilometres. Jupiter's fuzzy core, by the Juno measurements, is spread across a region more than twice the diameter of the entire Earth. Side to side, the implications of this are staggering. A compact core is relatively easy to explain. It is what you would expect if a rocky body gathered gas around it and remained intact at the centre. A dilute core implies something far more complicated. It implies that whatever rocky nucleus Jupiter may once have had has at some point in the planet's 4.5 billion year history been partially dissolved, mixed, blurred, smeared into the surrounding hydrogen until the boundary between core and envelope no longer meaningfully exists. The question then is how. Two competing theories emerged almost immediately. The first is a process called core erosion, a gradual dissolution driven by convective mixing in the overlying layers of metallic hydrogen. Under extreme pressures and temperatures, rock and metal can dissolve into metallic hydrogen with a slow but inexorable efficiency. Over billions of years, convective currents would carry this dissolved material upward, spreading it through progressively larger volumes of the interior, blurring the once distinct core boundary. This is a thermodynamic process, slow, patient, dictated by entropy. The second theory is more dramatic. In January 2019, a paper published by Shangfei Liu and colleagues in the journal Nature proposed that Jupiter's dilute core might be the result of a giant impact, a head-on collision with a massive protoplanet, perhaps 10 Earth masses, during Jupiter's early history. Such a collision would have deposited an enormous quantity of heavy element material deep into Jupiter's interior and stirred its interior so violently that the original compact core was disrupted. Its material mixed into the surrounding layers in a process called impact-induced envelope pollution. The smoking gun, the authors argued, was the specific distribution of heavy elements suggested by the Juno gravity data, a distribution that is more consistent with a single violent mixing event than with billions of years of gradual erosion. This idea was seized upon by the planetary science community with considerable excitement. A planet-sized impactor striking Jupiter in its early history would leave traces, not just in the interior structure, but potentially in the chemical abundances of the envelope. It connected Jupiter's mystery to the broader story of the chaotic early solar system, when planetary migration and giant impacts were reshaping everything. It was a compelling narrative, and for several years it commanded significant support. And then, in 2025, new simulations from Durham University delivered an uncomfortable verdict. The N-body modelling and impact simulations found that the specific distribution of heavy elements in Jupiter's interior, as reconstructed from the Juno gravity measurements, is not consistent with a single giant impact. The simulations could produce violent mixing, yes. They could produce a fuzzy core, in principle, but they could not produce the particular shape and extent of fuzziness that Juno measured. The Durham work concluded, in the careful language of scientific papers, that Jupiter's fuzzy core is not caused by an impact and is likely to be an outcome of its formation process. This is where we stand today. The core is fuzzy. We cannot fully explain why. The two leading explanations have each been challenged by the data, and meanwhile, a separate set of discoveries from the University of Edinburgh, published in November 2025, suggested that the question of what is in Jupiter's core might be even more complex than any of these models assumed. The Edinburgh team used quantum mechanical simulations to investigate how elements behave inside metallic hydrogen under the pressures and temperatures found in Jupiter's interior. Their findings were unexpected in the most specific possible sense. Almost all elements they found will dissolve readily into metallic hydrogen, not just iron and rock. Carbon, nitrogen, oxygen, these elements, the same elements that, at lower temperatures and pressures, combine to form the organic molecules that are the building blocks of life, are soluble in metallic hydrogen. And the team found something further, that carbon, nitrogen and oxygen, under metallic hydrogen conditions, can form stable, covalently bonded molecules they termed hypermolecules, exotic compounds with hydrogen contents far exceeding anything possible at ordinary temperatures and pressures. I will admit, when I first read that finding, I had to sit with it for a moment. The interior of Jupiter, the place we have always thought of as a furnace of crushing pressure and lethal heat, may be a cauldron of organic chemistry, the same planet that we think of as a gas ball, a hydrogen sphere with not even a surface to stand on, may contain, dissolved within its metallic hydrogen layer, the chemical precursors of biological molecules, not life as we know it, and almost certainly not life of any kind we can currently conceive, but chemistry of the kind that, at lower pressures and gentler temperatures, forms the basis of everything alive, which raises the question that the Edinburgh team themselves flagged. If organic molecules are soluble in metallic hydrogen and can survive inside Jupiter, what does that imply about the interiors of the hundreds of billions of gas giant exoplanets now known to populate the galaxy? Does this kind of chemistry happen everywhere? Is it common? Is the chemistry of life not confined to the surfaces of small rocky planets, but distributed throughout the bulk of every gas giant in the cosmos? We do not know, but the fact that the question is now scientifically legitimate, that it follows from laboratory-grounded physics rather than speculation, changes the landscape of what we consider possible. And that is, to my mind, one of the most consequential things Juno's measurements have set in motion. But the dilute core, as extraordinary as it is not the strangest thing beneath Jupiter's clouds. The magnetic field claims that title, and understanding what Juno found in Jupiter's magnetic field requires returning to the surface, metaphorically, and looking at something you can see in any good image of Jupiter's southern hemisphere, a feature that has been there for years, that looks like nothing else in the solar system, and that has a name as understated as it is incongruous. They call it the Great Blue Spot, and what it tells us about what is happening inside Jupiter right now, in real time, is genuinely disquieting. Before we descend into the magnetic field, into the Great Blue Spot, and everything it reveals, I want to stop for a moment and account for the human being who made this mission possible, because the Juno spacecraft did not emerge from an institution. It emerged from a decision made by one scientist, sustained over a period longer than most professional careers, against resistance that would have defeated most people before they got started. Scott Bolton is not a household name. He has never appeared on a late-night talk show, never had a viral moment, never written a best-selling book about his work. He is, by the measure of public profile, unremarkable, but in the specific world of planetary science, the small, intensely competitive, chronically underfunded domain of people who dedicate their careers to understanding other worlds, he is something close to a legend. Not for his charisma, for his persistence. Bolton first became interested in Jupiter's interior as a graduate student at the University of California, Berkeley, in the late 1980s. His early work focused on Jupiter's radiation environment, the belts of trapped energetic particles that make the Jovian system so hostile to spacecraft. He worked on the Galileo mission, contributed to Cassini's Saturn flybies, and throughout all of this maintained a specific scientific obsession. What is actually happening inside Jupiter? What is beneath those clouds? What generates that magnetic field? What is the core made of? The questions were not new. They had been asked for generations. But the means to answer them did not yet exist. In 1997, Bolton submitted a concept for a new Jupiter mission to NASA's New Frontiers program, a medium-class mission category designed to pursue high-priority science objectives at moderate cost. The concept was called Juno. Its central instrument, the one that would make it scientifically unique, was the microwave radiometer, an antenna system designed to penetrate Jupiter's clouds and measure temperature and composition at multiple depth levels simultaneously, exploiting the way water and ammonia absorb microwave radiation in the same way that a microwave oven heats food. It was at the time a genuinely novel application of radio frequency science to planetary exploration. Nothing like it had been sent to the outer solar system before. The proposal was not selected. NASA awarded Newfront funding to other missions. Bolton revised and resubmitted. The concept was evaluated, refined, discussed, and sent back. The years passed. Colleagues moved on to other projects. The institutional patience required to maintain a single proposal through multiple competitive cycles, each lasting several years, across more than a decade, is of a kind that most people, scientists included, find difficult to sustain. Bolton sustained it. In 2005, Juno was selected as the second mission in the New Frontiers program. The spacecraft would not launch until August 2011. It would not reach Jupiter until July 2016. From the moment of Bolton's first concept submission to the moment of arrival at the planet, 19 years had passed, but the challenges did not end with selection. During development, the mission budget came under pressure. At one point, there were serious discussions about whether the spacecraft was too expensive to continue. Bolton fought for it. In meetings, in budget reviews, in the particular bureaucratic trench warfare that characterises the survival of any large science mission through the political cycles of government funding. Mission survived those reviews. And then in 2016 came the moment that concentrated nearly 3 decades of effort into a single night. Jupiter Orbit Insertion, GOA, occurred on July 5, 2016. For Bolton and his team at the Southwest Research Institute in San Antonio, and for the mission operations team at NASA's Jet Propulsion Laboratory in Pasadena, it was the most precarious hours of the entire project. To break into orbit around Jupiter, Juno had to fire its main engine for 35 minutes, a burn that would slow the spacecraft from its approach velocity enough for Jupiter's gravity to capture it. If the burn was too short, Juno would sail past Jupiter and never return. If the engine misfired, or if any of a dozen other critical systems failed, years of work would vanish into the void in a matter of seconds. And there was another complication: Jupiter's radiation environment. The environment Bolton had spent years of his early career characterizing was the greatest threat. Juno's polar approach was specifically designed to thread it past the most intense radiation zones, but the orbit insertion trajectory still passed through regions of significant particle flux. The radiation vault was protecting the electronics, but no one had truly proven that the vault was sufficient, because no spacecraft had ever survived a close Jupiter orbit before. The titanium shielding was calculated to work. Calculations and reality sometimes disagree. At 11:53 p.m. Pacific Time on July 4, 2016, deliberately timed to the Independence Day holiday so that controllers could be at their consoles, Juno began its engine burn. For 35 minutes, the spacecraft was out of contact with Earth, hidden behind Jupiter, firing its engine in complete communication blackout. The signal travel time from Jupiter to Earth was approximately 48 minutes. There was nothing to do but wait and calculate and try not to think about what failure would mean. The tone came back at 11:53 p.m. Pacific Time. a single radio carrier tone, unmodulated but present, the signal that Juno was alive, that the burn had completed, that the spacecraft was in orbit. The control room erupted. People who had spent decades working toward this moment wept without embarrassment. Bolton, speaking to reporters that night, chose the word that his entire career had been aimed at. "We're there." Just that. No elaboration. 27 years of work, and the man who had driven the mission to existence said 2 words and went back to watching the data. What that data would reveal in the coming months and years would repay every year of effort 1,000-fold. And it would do so in ways that even Bolton had not anticipated, because the magnetic field that Juno's magnetometer suite began mapping on the very first close pass over Jupiter was not the field any of the models had predicted. It was something that, by rights, should not have been there. A feature so anomalous that the Juno team, when they first saw it in the data, went back and checked their instruments before accepting it was real. The Great Blue Spot. An intense, localized concentration of magnetic flux near Jupiter's equator. A patch of field so anomalously powerful, so out of place in the overall structure of the planet's magnetosphere, that it demands its own chapter in the story of what lies beneath those clouds. And what it reveals about Jupiter's interior is not merely peculiar. It is, if you follow the implications far enough, a window into a process happening inside the planet right now, in real time, at depth we cannot directly observe but can, thanks to Juno, finally begin to understand. Let me begin this chapter with a claim that sounds like it should be impossible, and then explain why it is not only possible, but measured and confirmed. Jupiter's magnetic field is changing. Not over millions of years, not over geological timescales. It is changing in ways that were measurable across the roughly 5 years of Juno's primary mission, between 2016 and 2021, a blink of an eye in planetary terms. And the thing that is driving those changes is a connection between the surface weather and the deep interior that nobody predicted. To understand the Great Blue Spot, you need to understand that Jupiter's magnetic field, as mapped by Juno in full detail for the first time, is not a simple dipole like Earth's. Earth's field, in its basic structure, resembles the field of a bar magnet, a north magnetic pole, a south magnetic pole, field lines looping cleanly between them. Jupiter's field is nothing of the sort. It is lumpy, asymmetric, chaotic in a very specific technical sense. It contains features at a wide range of scales, from large, planet-wide structures down to concentrated local anomalies that are geographically confined but locally intense. The most notable of these anomalies is the Great Blue Spot. The name, coined by the Juno magnetometer team under Jack Connerly at NASA's Goddard Space Flight Center, refers to a mapping convention. In the field maps, regions of intense magnetic flux pointing into the planet are coloured blue, and the Great Blue Spot is a region near the equator, at approximately 80 degrees west longitude in the Jovian coordinate system, where the field is locally several times stronger than average. It is, in essence, a magnetic bruise, a concentrated patch of intensity sitting in a part of the planet where, by the smooth predictions of simple dynamo models, the field should be relatively mundane. What makes the Great Blue Spot scientifically extraordinary is not merely its existence, it is the fact that it is moving. And it is being moved by something specific, the jet streams. Jupiter's equatorial jet stream, the fastest and most energetic wind band on the planet, blows eastward at speeds approaching 500 kilometers per hour. Juno's measurements showed that this jet stream does not confine itself to the upper atmosphere. It reaches down, as we discussed, to depths of roughly 3,000 kilometers, and at those depths, it encounters Jupiter's electrically conducting interior. A conducting fluid moving through a magnetic field carries that field along with it, stretching and distorting the field lines in a process called magnetic advection. The Great Blue Spot is being stretched. The eastward jet stream to its north pulls it east. The westward winds to its south pull it west. The result over the years of Juno's observations is that the anomaly is being elongated, its edges being smeared in opposite directions by the differential winds. And because the bulk of the Great Blue Spot, is being carried along by the net eastward drift of Jupiter's equatorial flow, the entire feature migrates eastward relative to the planet's interior, completing, Conony's team calculated, a full circuit of Jupiter approximately once every 360 years. This is a detection of something extraordinary: the direct coupling between Jupiter's surface weather and its deep magnetic interior, the winds you can see in Jupiter's cloud bands. In the brown belts and white zones that have been observed since the 17th century, are physically dragging the magnetic field of the planet's interior. The surface and the deep interior are not separate systems, they are mechanically linked through the electrical conductivity of the metallic hydrogen layers across thousands of kilometers of depth. And Juno also found something that the pre-mission models had explicitly not predicted: a fourth magnetic pole. Earth has two magnetic poles, a north and a south, as you would expect from a dipole field. Jupiter has at least four, two conventional poles near its geographic poles, and two additional, weaker poles in other locations that indicate a more complex, higher-order structure to the field than any simple dynamo model had suggested. This additional complexity tells us that the dynamo generating Jupiter's field, the convective region of metallic hydrogen in which electric currents flow and sustain the magnetism, is itself non-uniform. It is not a simple shell of conducting fluid behaving identically at all latitudes. There are structural variations, possibly connected to asymmetries in the temperature, composition, or flow patterns of the metallic hydrogen layer, that produce this complex multipole structure. This discovery had implications that extended beyond Jupiter. Gas giant magnetism is relevant to the study of exoplanets, the thousands of Jupiter-sized and larger worlds orbiting other stars that have been catalogued by Kepler, TESS, and ground-based surveys. Many of those worlds are hot Jupiters, gas giants orbiting far closer to their stars than Jupiter orbits the Sun, exposed to intense stellar radiation that strips their atmospheres and interacts violently with their magnetic fields. Understanding how gas giant dynamos actually work, not just in theory but from direct measurement, is essential to understanding the behaviour of those worlds, and in turn to understanding what happens to atmospheres when magnetic fields are weakened or absent. Magnetic fields protect planetary atmospheres from stellar wind erosion. A planet that loses its magnetic field tends to lose its atmosphere too. The fate of potentially habitable worlds is intertwined with the physics of their magnetic dynamos. Jupiter is the only gas giant we can study up close. Every measurement Juno makes of Jupiter's magnetic field contributes directly to models of gas giant magnetism that apply across the galaxy. But there is yet another layer to this story, and it involves water, not as an abstract chemical abundance, but as a physically present, meteorologically active substance that Jupiter is generating inside its clouds in a way that no one had predicted. A substance that falls not as rain and not as snow, but as something that has no direct analogue in Earth's weather, and that carries, dissolved inside it, one of the most reactive chemicals in the outer solar system. The Juno team called them mushballs. The name is not entirely a joke, though it is admittedly more whimsical than the discoverers of a novel planetary weather phenomenon might typically choose. But the mechanism they describe is real, and the consequences of their existence for our understanding of Jupiter's interior reach all the way down to the dilute core. In August 2020, two papers published simultaneously in the journal Nature described a discovery that completely overturned the expected picture of weather in Jupiter's upper atmosphere, and in doing so provided a new mechanism by which material is moved between the different layers of the planet on a continuous planetary-wide basis. The story begins with lightning. Jupiter has lightning. This was known since the Voyager spacecraft detected radio emissions characteristic of lightning during its 1979 flyby. Lightning requires moisture. You need water droplets and ice crystals in a convective cloud to separate electric charge and produce the enormous voltage differentials that discharge as a bolt. Jupiter's lightning, therefore, confirmed the presence of water clouds even though the Galileo probe had found far less water than expected. The lightning was there, the water had to be there. The Galileo probe, the community agreed, had simply been unlucky in its sampling location. But Juno found something unexpected in Jupiter's lightning distribution. Using its radio detection instrument, the spacecraft mapped the global distribution of lightning on Jupiter with a completeness that previous missions could never achieve. And what the map showed was a paradox. Jupiter's lightning was clustered as expected in convective storm regions, but it was entirely absent from a very specific zone of the upper atmosphere, the ammonia-rich layer from roughly 5 to 20 bar pressure, where by any reasonable meteorological expectation you should find some of the most active convection on the planet. The absence of lightning from the ammonia layer was not just puzzling, it was deeply puzzling in a way that suggested something was actively preventing normal lightning-generating convection in that zone. And the explanation that Juno scientists Tristan Guillot, Scott Bolton, and their colleagues arrived at was something that, on first reading, sounds like a mistake. The ammonia in Jupiter's upper atmosphere, they proposed, is not behaving like a gas. It is behaving like a solvent. Water ice particles forming in Jupiter's cold upper atmosphere fall downward through the temperature gradient. As they descend, they enter the ammonia cloud layer, roughly 60 kilometers below the visible cloud tops, where the temperature is around 176 Kelvin, minus 97 degrees Celsius. At this temperature, something chemically extraordinary happens. Liquid ammonia, which freezes at a lower temperature than water, coats the falling water ice particle, creating a mushy, slushy mixture of ice and liquid ammonia. The liquid ammonia begins dissolving the water ice, producing a solution that has thermodynamic properties quite different from either substance in isolation. This slush ball then continues to fall, picking up more ammonia, growing in size, and eventually producing a hailstone-like object that can be anywhere from the size of a golf ball to the size of a grapefruit, a dense ammonia water slush core covered in a shell of ice that the Juno team termed a mushball. Mushballs fall fast. They are denser than the surrounding atmosphere, heavy enough to punch through wind shear that would deflect lighter particles. As they fall, they carry their dissolved ammonia load downward, transporting material from the high-altitude ammonia cloud layer deep into the planet's atmosphere to depths far below the cloud tops, when they eventually evaporate. As the temperature and pressure increase with depth, they deposit their ammonia load into the lower atmosphere, creating a distinct ammonia depletion in the upper layers that Juno's microwave radiometer had actually measured years before the mushball mechanism was proposed to explain it. This is the ammonia depletion paradox. Juno's microwave measurements showed that Jupiter's upper atmosphere is surprisingly poor in ammonia in many regions, not because Jupiter doesn't have ammonia, it manifestly does. The visible cloud layer is made of ammonia ice, but because something was removing it from the upper atmosphere and carrying it downward. The mushball mechanism provides the transport pathway. It is meteorological conveyor belt chemistry, a weather system that moves material vertically through the atmosphere on a planetary scale, mixing layers that simple diffusion would never connect. This has direct implications for the water abundance question that the Galileo probe raised, and Juno's microwave measurements began to address. If ammonia-laced hailstones are efficiently transporting material between atmospheric layers, then simple depth profile measurements of atmospheric chemistry may be systematically misleading. The atmosphere is not well mixed, as simpler models assumed. It is dynamically stratified by active transport mechanisms we did not know existed before Juno, because no instrument before Juno had the penetrating power to see beneath the clouds where the chemistry was happening. Juno's microwave radiometer eventually found that water abundance at Jupiter's equator is approximately 0, 25% of the total atmospheric molecules, roughly 3 times the solar value, which is the abundance expected if Jupiter incorporated material from the same reservoir as the Sun. This is a fundamentally important number. It suggests that Jupiter's interior is water-enriched relative to the Sun, consistent with the planet having accreted significant quantities of ice and rock from the cold outer solar system. It is consistent with core accretion models in which the nascent Jupiter swept up icy planetesimals during its formation. But the measurement is equatorial only. The water abundance at other latitudes, at the poles, in the belt and zone regions, is still being characterized. And the mushball mechanism means that measurements at any single depth may not represent the true bulk abundance, because ammonia transport is actively redistributing the atmospheric inventory in ways we are still working to fully quantify. The Juno team also found, in the storm regions associated with mushball formation, a phenomenon they termed shallow lightning, electrical discharges occurring at much higher altitudes in the atmosphere than classical Jovian lightning, at the boundary between the water cloud and the ammonia water slush zone. Shallow lightning is generated not by the large-scale convective towers that produce classical lightning, but by the charge-separating interactions between falling mushballs and the surrounding cloud particles. It is a distinct electrical phenomenon, and its existence independently confirms the physical reality of the mushball mechanism. I find this detail, the existence of shallow lightning, as a fingerprint of a meteorological process, scientifically beautiful in a specific way. It illustrates how, in planetary science, a single observation can simultaneously confirm a mechanism, constrain a model, and open 3 new questions. The shallow lightning is evidence for mushballs. The mushballs are evidence for the ammonia transport mechanism. The ammonia transport mechanism is evidence that Jupiter's interior is less well-mixed than any model predicted, and a less well-mixed interior raises questions about the reliability of every compositional measurement ever made of this planet. Each answer is a door, and the door opens onto a room full of other doors. Now let us talk about the poles, because the poles of Jupiter, the regions that no spacecraft had ever seen before Juno, because every previous mission had approached from the equatorial plane, turned out to contain one of the most geometrically extraordinary structures in the solar system. A structure that has, since its discovery, generated theoretical papers, controversy, and a level of genuine scientific perplexity that is unusual even by the standards of Jovian research. When Juno swept over Jupiter's North Pole on its very first close pass in August 2016, the infrared camera known as the Jovian Infrared Auroral Mapper, GIRAM, provided by the Italian Space Agency, returned an image that stopped the science team in their tracks. Instead of the swirling, chaotic texture of the lower latitude atmosphere, the North Pole was occupied by a vast, organised geometric structure, a single central cyclone, surrounded by 8 more cyclones arranged in a near-perfect octagonal pattern. 8 storms, each one the size of a continent, arranged symmetrically around a central vortex. The South Pole had a different but equally ordered structure. 1 central cyclone surrounded by 5 more in a pentagonal arrangement. This was not expected. This was not anything like what models of atmospheric dynamics had predicted for a planet rotating as fast as Jupiter. Jupiter completes a full rotation every 9 hours and 55 minutes, fastest rotation of any planet in the solar system. Rapidly rotating planets are expected to have turbulent, chaotic polar regions, not elegant polygonal arrays of organised storms. The analogy most frequently invoked for planetary polar vortex patterns was Saturn, but Saturn's poles have a single, well-defined hexagonal jet stream, not an ensemble of discrete storms arranged in geometric formation. Jupiter's polar polygons were, and to a significant degree remain, something outside the existing frameworks. What keeps them stable? Why don't they merge? A single cyclone encountering another should, in principle, either absorb the weaker one or be deflected. But Jupiter's polar cyclones are locked in their positions, bouncing off each other like springs in a mechanical system, as Juno investigator Yohai Caspi of the Weizmann Institute of Science described in 2025, slowly drifting westward around the pole, but maintaining their geometric integrity across years of observation. The mutual interactions between the storms, the way each cyclone's wind field exerts force on its neighbours, appear to create a collective stability that neither merges the storms into one nor allows them to drift apart. It is a self-organising system of atmospheric dynamics, operating at a scale that has no precedent in the solar system we thought we understood. New cyclones have been observed forming and joining the polar arrays. On one occasion, Juno documented the South Polar Array changing from 5 circumpolar cyclones to 6. A new storm, the size of the state of Texas, forming in the outer ring and being incorporated into the existing geometric structure. The array expanded to accommodate it. Then, years later, a separate observation suggested the South Polar pattern might be adjusting back. The system is dynamic. It is alive, in the meteorological sense, and it is governed by a physics we are still in the process of articulating. The polar discoveries, the mushball mechanism, the jet stream depth, the dilute core, the magnetic great blue spot, the secular variation of the magnetic field, each of these is a result of Juno's instruments penetrating deeper beneath Jupiter's clouds than any previous technology allowed. And they connect, in ways that are still being worked out, into a coherent picture of a planet that is far more dynamically active, far less well separated into neat interior shells, and far stranger than any of the textbook models described. But there is one more frontier that Juno's measurements have opened. A frontier that connects Jupiter not just to the history of our solar system, but to the future of planetary science across the galaxy. And it begins with a question that until very recently would have seemed too speculative to ask in serious scientific company. Is there a way that the chemistry happening inside Jupiter, the chemistry of dissolved metals, organic hypermolecules, and metallic hydrogen, tells us something fundamental about the distribution of complex chemistry in the universe? The Juno mission was, formally, a mission to understand Jupiter. But as is so often the case in planetary exploration, understanding one world means developing tools, frameworks, and questions that illuminate a much broader canvas. Every discovery Juno made about what lies beneath Jupiter's clouds, the dilute core, the magnetic complexity, the deep jet streams, the polar polygons, the mushball chemistry, forces a revision not just of our model of Jupiter, but of our model of giant planets everywhere. Consider the dilute core. Before Juno, the core accretion model, in which a solid rocky core gathers hydrogen from the surrounding nebula, was the dominant framework for explaining how gas giant planets form. The core was expected to be compact and distinct. Juno showed that Jupiter's core is neither. If the solar system's best-studied gas giant lacks a well-defined solid core, what does that imply for the thousands of gas giant exoplanets we have detected around other stars? Their interiors, which we cannot currently measure with anything like Juno's precision, may be similarly diffuse. The models we use to infer interior structure from the limited data available, primarily mass and radius measurements, supplemented occasionally by transit spectroscopy of atmospheres, may be systematically wrong in the same direction they were wrong for Jupiter. The Edinburgh University findings about metallic hydrogen solubility extend this uncertainty in a direction that is simultaneously unsettling and exhilarating. If heavy elements, including carbon, nitrogen, and oxygen, dissolve readily into metallic hydrogen, then the interiors of giant planets are not inert compressed gas interiors. They are chemically active environments. The boundary between rocky core and gas envelope is not a clean line but a gradient, a zone of continuous chemical exchange, where elements dissolve, convect upward, and alter the composition of successive layers. This means that the atmosphere we observe at the top of a gas giant's cloud deck is not merely a representation of the planet's primordial composition. It carries a chemical signature of the interior chemistry, modified by billions of years of convective exchange. This has immediate relevance to the emerging field of exoplanet atmospheric characterization. The James Webb Space Telescope, now operating in full science mode, returning spectra of exoplanet atmospheres with a precision that Hubble could not approach, is detecting chemical abundances in the atmospheres of gas giants around other stars. Molecules of water, carbon dioxide, methane, ammonia, and sulfur dioxide have been detected in exoplanet atmospheres. Those abundance measurements are being used to infer things about the planet's formation history, its bulk composition, and its interior structure. But if the Edinburgh findings are correct, if the metallic hydrogen interior acts as a solvent that continuously dissolves and redistributes chemical elements throughout the planet's bulk, then the simple relationship between atmospheric abundance and bulk composition breaks down. The atmosphere of a gas giant is not a direct window onto its formation chemistry. It is a window onto a system in dynamic chemical equilibrium with a metallic hydrogen interior, and that interior is dissolving things in ways we have only begun to characterize. The hypermolecule findings add another layer: carbon, nitrogen, and oxygen, the three elements that combined with hydrogen constitute almost all known organic molecules, are stable in metallic hydrogen under Jovian interior conditions. They form exotic compounds that have no analogues in ordinary chemistry. These compounds exist at pressures of hundreds of millions of atmospheres and temperatures of tens of thousands of Kelvin. They cannot be extracted and examined in a terrestrial laboratory under those conditions. They would simply decompose the instant the pressure dropped. But they exist. They are not theoretical curiosities. They are the product of quantum mechanical simulations that are grounded in the same physics that accurately describes metallic hydrogen in every other context we can test. What this means for the question of life's cosmic distribution is genuinely uncertain, and I want to be careful not to oversell it, because overselling speculative science is how credibility is squandered. No one is suggesting that Jupiter is inhabited. No one is proposing that there are organisms dissolved in the metallic hydrogen layer. The temperatures and pressures there are incompatible with any biological process we know of, and there is no reason to think they are compatible with any biology we don't yet know of. But the chemistry of life, the arrangement of carbon, hydrogen, nitrogen, and oxygen into stable, complex molecular structures, appears to be possible inside giant planets. Under conditions of extreme pressure and temperature, organic chemistry does not shut down. It continues in a radically different register. This expands the conceptual space in which we look for chemistry that might, under some circumstances, lead to complexity. It means that giant planets are not chemically barren interiors. They are chemically active ones, and there are a lot of giant planets. Estimates of the number of gas giant planets in the Milky Way alone range from hundreds of millions to over 1 billion. If each of those planets contains a metallic hydrogen layer in which organic hypermolecules are continuously forming and dissolving, then the total mass of complex organic chemistry in the galaxy is not concentrated on the surfaces of small, rocky, potentially habitable worlds. It is distributed throughout the bulk of every gas giant in every planetary system in the cosmos. The universe is, in this reading, far richer in complex chemistry than we had previously assumed. This is not a conclusion, it is a question. But it is a question that could not have been asked before Juno, because before Juno, we did not know what was beneath Jupiter's clouds, with sufficient precision to ground such speculation in physical measurement. The speculation was always possible. The physics supporting it was not. Juno's mission has been extended multiple times beyond its original primary phase. As of 2025, the spacecraft continues to orbit Jupiter, conducting radio occultation soundings of the atmosphere, mapping the polar cyclone dynamics with each new pass, monitoring the secular variation of the magnetic field, and flying close to Jupiter's moons, including Io, where Juno discovered in late 2024 and early 2025 the most powerful volcanic eruption ever recorded on that moon, a continuous lava outpouring that was still active as of March 2025. Juno has become, in a sense, a mission to the entire Jovian system, a system that now includes new measurements of Ganymede's ice shell, Io's subsurface lava fields, and Europa's potential subsurface ocean, all gathered by a spacecraft that was originally designed to measure only what lay beneath Jupiter's own cloud tops. The mission will eventually end. Jupiter's radiation environment will accumulate sufficient damage to compromise the spacecraft's operations. And at that point, as with Galileo before it, Juno will be directed into Jupiter's atmosphere to ensure it does not contaminate any of the moons, particularly Europa, which may harbour liquid water and is therefore treated with the same biological caution we apply to Mars. When Juno enters Jupiter's clouds, it will experience the same ferocious deceleration heating that destroyed the Galileo probe in 2003, a controlled, deliberate end for a spacecraft that has spent years probing those same clouds from above. But before that end comes, Juno will continue returning data, and that data will continue feeding into models of Jupiter's magnetic field evolution, of its interior structure, of the chemical exchanges between layers, of the polar cyclone dynamics. That will take decades of analysis to fully interpret. The primary scientific findings we have discussed in this script represent the first wave of results from an instrument suite that is still, in 2025, collecting measurements that have not yet been published. There are things in Juno's data that scientists are still working to understand. There are results that have been flagged as unexpected, but not yet fully explained. There are anomalies in the magnetic field maps that the current dynamo models cannot account for. The story of what NASA found hiding beneath the clouds of Jupiter is not finished. It will not be finished when Juno burns up in those clouds. It will not be finished when the next Jupiter mission, the European Space Agency's JUICE spacecraft, currently en route to the Jovian system, expected to arrive in 2031, begins its own observations. It will not be finished when NASA's Europa Clipper completes its planned flybys of Europa in the 2030s. The story will be carried forward by the scientists who are, right now, completing their doctorates on Juno data, who will spend the rest of their careers asking the questions that Juno's answers have generated. The dilute core that Juno found is not the end of the investigation into Jupiter's formation. It is the end of the era in which we didn't know the question precisely enough to investigate it properly. We now know that the core is fuzzy. We now know the approximate spatial extent of that fuzziness. We do not know why, not with the certainty that science requires before a question is considered closed. The next generation of instruments, the next generation of orbital mechanics, the next generation of quantum simulation methods, they will all be aimed in part at the specific, precise, well-defined mystery that Juno bequeathed to planetary science, the magnetic field that Juno mapped, the field with its extra poles, its great blue spot, its measurable secular variation, is a snapshot of a process that is ongoing. The field is changing now. The winds are dragging it eastward now. The metallic hydrogen is conducting, convecting, generating magnetic flux now. A future mission with a magnetometer more sensitive than Juno's, in an orbit that permits more frequent and more detailed field mapping, will be able to trace the evolution of Jupiter's magnetic dynamo over the next several decades. Watching a planetary magnetic field evolve in real time in a way that has never been achieved for any world in the solar system, including our own, and the question of what the Edinburgh hypermolecules mean. Whether organic chemistry inside metallic hydrogen is a universal feature of gas giant interiors, how those molecules interact with the overlying layers, whether they carry any traceable signature in the atmospheres we observe, is a question that will drive a new generation of high-pressure physics experiments, quantum simulation studies, and exoplanet observation programs. It is a question that sits at the intersection of planetary science, chemistry, and the origin of life, which means it attracts funding, talent, and attention from 3 different scientific communities simultaneously. That attention will produce results on timescales of years to decades. There is a concept in science called the adjacent possible, coined by the complexity theorist Stuart Kauffman to describe the set of things that become possible as soon as a discovery is made. Each discovery opens a door to a room containing other doors, and the boundaries of the adjacent possible expand with every measurement that reveals something new. Juno has, in 8 years of orbiting Jupiter, expanded the adjacent possible of planetary science by an amount that will take decades to fully explore. The dilute core was not just a discovery, it was a key that unlocked a new room in our understanding of how planets form. The Great Blue Spot was not just an anomaly, it was a demonstration that gas giant magnetic fields are living systems, not static structures. Mushballs were not just an oddity of Jovian meteorology, they were a proof of principle that weather on a gas giant operates through mechanisms with no terrestrial analogue, and that any simple extrapolation from Earth's atmosphere to other worlds is likely to be systematically wrong. Stand for a moment at the top of Jupiter's cloud deck. Not in any physical sense, no human being has stood there, and none will within any time frame worth imagining. But in the imagination, which is where all of this begins, and where much of it still resides. You are looking out across an ocean of ammonia ice crystals, blinding white where the sunlight catches them, shading into cream and orange and rust, where the chemistry darkens the clouds with organic tars and sulfur compounds. Below you, the clouds descend into pressure and heat for thousands of kilometers, down through mushball storms and shallow lightning, down through the water layers, down through the layer where hydrogen becomes first liquid and then metallic, where it loses its ordinary identity as a gas and becomes something with no terrestrial name, something that conducts electricity and flows like a fluid and carries organic molecules dissolved in its bulk. And then, at depths that no probe has ever directly measured, the metallic hydrogen gives way to whatever lies at the centre, the diffuse, blurred, dissolved remnant of whatever seed existed at the beginning of this planet's history, spread across tens of thousands of kilometres like a flavouring dissolved into an enormous pot, inseparable from the bulk. And yet still, somehow there, Jupiter does not have a heart in the way we imagined. It has something more subtle, a gradient, a signature, a memory of its origin, written in the distribution of heavy elements throughout its interior, legible only to instruments of extraordinary precision flying in orbits that took 27 years to propose, fund, build and execute. The universe, I think, does this to us on purpose. Or not on purpose. There is no purpose in physics, but with the consistent effect of reminding us that the model is not the territory. We build elegant theories, we construct clean cross-sectional diagrams in textbooks, we name the layers and assign the temperatures, and declare the structure understood, and then we send a spacecraft close enough to actually measure, and the planet looks back at us with something that in any other context we might call amusement. The interior is not compact, the core is not solid, the magnetic field has extra poles, the storm goes down 500 kilometres, the hailstones carry ammonia. There are organic molecules in the metallic hydrogen. Every time we approach a world, truly approach it, with instruments that can penetrate its screens and measure what it has always been, we discover that reality is more complicated, more layered, more dynamic than our most ambitious theories allowed. And every time that happens, we do not retreat. We revise, we build the next mission, we hire the next generation of scientists to ask the next set of questions, which are always more precisely framed than the previous generation's questions, because the previous generation's answers narrowed the field of productive inquiry and opened new directions of productive uncertainty. Scott Bolton called Jupiter the Rosetta Stone of the solar system, the key that, when properly read, should decode the language in which the history of our cosmic neighbourhood is written. That is a beautiful metaphor, and it is accurate. But the Rosetta Stone was, when Champollion finally cracked it, a finished object, static, carved, complete. Jupiter is nothing of the sort. Jupiter is a Rosetta Stone that is still being written, whose text is still evolving, whose script changes as the magnetic field drifts and the core slowly mixes, and the polar cyclones oscillate in their geometric arrangements, and the mushballs fall and dissolve and deposit their chemistry in layers we have only begun to sample. What NASA found hiding beneath the clouds of Jupiter was not a single thing. It was a complexity that our instruments, for the first time, were sufficient to begin measuring. It was evidence that the solar system's largest planet is alive, in the geological sense, dynamically active, chemically evolving, magnetically changing. and it was evidence that the universe is, at its chemical foundations, richer and stranger than the life sciences, and the planetary sciences had separately assumed. There is a generation of scientists working right now, graduate students, postdoctoral researchers, early career faculty, who will spend their professional lives following the questions that Juno generated. They will build the instruments that answer the questions Juno could only frame. They will fly the missions that reach the depths Juno could only infer. They will stand in the control rooms of spacecraft we have not yet designed, watching data return from planetary interiors we have not yet visited, and they will feel the particular, irreplaceable sensation of having the universe surprise them. I find it genuinely moving that this is how science works. Not as an accumulation of certainties piling up until the mystery is exhausted, but as an accumulation of better questions, each answer opening a room full of doors, each door leading to a corridor with more doors still, the building expanding as fast as we explore it, always larger than it was when we walked in. Jupiter is not understood. Jupiter is for the first time sufficiently measured that we know precisely what we do not understand, and that precise, well-defined, instrument-grounded not knowing is the most productive state a scientific field can occupy. The planet has been there for 4.5 billion years, holding its secrets beneath those clouds. We have been looking for roughly 4 centuries. Juno gave us 8 years of answers, and the answers have given us, if we are honest about it, the next 100 years of work. The clouds are still there. The core is still dissolving. The great blue spot is still drifting eastward, slowly, at 3.8 centimeters per second, circling a planet that began when the solar system was young, and will be there long after every institution we have built to study it is gone. Ask the question. Keep asking it, someone will carry it further.